Well, thank you. It's great to be here, and great to see all the activity that's an interest that's going on in this direction. So I'll give you an update on constructing local bulk observables. This is work in progress with Kabat Lifshitz, and there's been related works by many other authors. And I guess the title I gave to Steve was an update on constructing these observables. I kind of like the way that Daniel said it yesterday, going from CFT correlators to bulk Lagrangians. And well, I hope to convince you that that's what we're doing. So a little bit of motivation. What I'm going to assume is that we're starting from a CFT that's exactly soluble. At least in principle, we can calculate whatever we want in the CFT to whatever accuracy we need. Of course, that's solving the CFT is an interesting challenge, but that's not the problem I'm going to focus on. I'm going to assume we can solve the CFT exactly. And then what I'd like to do is formulate the problem of reconstructing bulk physics as a kind of a precise mathematical problem, something where you have a well-defined math problem that you just need to solve. So you don't really need to think. You just have to solve this problem. And I also hope to convince you that it's actually a problem you can solve systematically in the 1/n expansion. And so I'll tell you about results in this direction. And then the interesting stuff to speculate is, what happens at finite n if you go beyond the 1/n expansion, and can you say things about black holes or physics that's not perturbative in 1/n?
So when you say exactly soluble, you mean just that someone hands you all the correlators or something like that? You mean more?
Yeah, so in practice, I'd like someone to hand me all of the correlators in the CFT as exact analytic functions.
Great.
So the kind of simplest context to think about these things is ADS2 CFT1. If there's a massless scalar field in the bulk, and that field in the bulk would be dual to a single trace dimension 1 primary field in the conformal quantum mechanics. And just to get started, let's imagine we look at the CFT in some infinite n limit. In that limit, the CFT only has 2-point functions. So in a sense, it's a free CFT. And in this lit, what we'd like to be able to do to reconstruct the bulk is just express a free bulk scalar field in terms of the operator in the CFT. And that's a pretty easy problem to solve. It was solved long ago. You want to solve a massless wave equation in the bulk. You want to impose some appropriate boundary conditions that your bulk field falls off like z times your operator in the CFT as you approach the boundary. And, well, those are the equations you need to solve. Here's the solution. It expresses the bulk field in terms of your boundary operator smeared over some interval in the time direction.
This is a classical bulk here at the moment?
I'm working in the infinite n limit, so it's a classical bulk theory. It's a free bulk theory. This is pretty straightforward. This sort of construction generalizes. You can do something similar in higher dimensional ADS. You can do it for fields with spin. You can work it out in other coordinate systems. And I think Daniel and Vlad are going to tell us about some of the interesting things that happen when you think about reconstructing bulk physics using other coordinate patches.
What about the question of gauge choices in the bulk for fields with spin? I mean, the gravitational and photon fields.
Yeah, that's right. So if you want to play this game with for fields with spin, then the simplest thing to do is to fix a gauge in the bulk. So if you want to reconstruct a bulk gauge field from a current in the CFT, the simplest gauge choice is to set the z component of the gauge field to 0. So you reconstruct your bulk gauge field in something like that.
Is that a unitary gauge in the bulk field theory?
It's like axial gauge.
It's essentially axial gauge.
So it's a unitary.
Yeah, it's a unitary, you only have physical degrees of freedom in the bulk.
You only have physical degrees of freedom on the boundary.
Yeah.
Right, exactly. And there's a similar gauge choice for the metric where you set the HZZ and HZU components of the metric to 0.
But then the question arises in axial gauges in the bulk, we don't have local fields, right? Because there are non-local interactions.
Yeah, there are. Bulk fields, if you like, have Wilson line tails that extend off to the boundary in the z direction.
Right.
So there are non-local commutators. That all works out very neatly. There's a nice story. So the story that I'll tell you today is about trying to enforce bulk microcausality. And I'll show you how you do that mostly for scalar fields. When you're dealing with fields with spin, it turns out the ward identities in the CFT, those restrict CFT correlators in exactly such a way that they're an obstruction to enforcing bulk microcausality. And you get exactly the non-local commutators that you'd expect from the bulk Gauss constraints. So there's kind of a neat story how that works out. Story for another day, though.
I'll say a little about it, probably.
But that should presumably at higher orders, infect the scalar fields as well, right? Because they interact with the gravitational.
Yeah, it does. That's right.
Okay. All right. Haven't kept up with that. Thank
you. So what about interactions? Well, various approaches for including interactions have been discussed. I guess those are two of the references. And the approach that I want to focus on today is one where you take bulk locality or bulk microcausality as your guiding principle. So what's the idea there? We're going to start from a correlation function in the CFT. So this is some CFT 3-point function. Let's imagine that we apply one of these smearing kernels to the first operator in this correlator. So that should turn it into a field somewhere in the bulk. So now we've got a mixed correlator with one bulk field and two operators on the boundary.
You're now at finite end?
Well, let's see. So if I was doing this in the 1 over n expansion, this 3-point correlator would be order 1 over n. So yeah, I have gone to a subleading order in the 1 over n expansion. So the 3-point correlator, its form is fixed by conformal invariance. You also know these smearing kernels explicitly, so you can just do this integral. You get an answer that depends on, it's convenient to work in terms of this variable chi. So this is it's an ADS invariant cross ratio that depends on one bulk point and two boundary points. Let's see, so chi vanishes if your bulk point is light-like separated from the second boundary point, It also vanishes if your bulk point is light-like separated from the third boundary point, and it diverges when the two boundary points are light-like separated. But if these 3 points are all at space-like separation, then all of these factors are positive. So chi is positive at space-like separation, and that will be important in a minute. So you go ahead and calculate what you get for this mixed bulk boundary correlator. You find that it's given by a hypergeometric function. And I should say this is a result that's true in general dimensional ADS and also for scalar fields of arbitrary dimension.
By the way, I guess at this point, well, K is the thing that's constructed from the free Green's function, the space-like Green's function.
That's right.
So this is a function of X. Once you hit it on the 3-point function is non-normalizable, I guess.
No, K constructs normalizable fields in the bulk.
Only if it hits bulk fields that satisfy, say, the free equation of motion, I think.
Let's see, it's hitting a boundary operator.
Well, if it acts on a generic function on the boundary, then it constructs non-normalizable things. That's just, you can see that directly from the form of K if you look at the explicit formula.
No, I don't think so. I mean,
No, it's interesting.
so here's an explicit expression for K. And if I send Z to 0, if I go to the boundary, then...
Yeah, this is in 1 plus 1, isn't that? Is that non...
It doesn't look too different, I think, in higher dimensions.
Yeah, no, well, again, if you look it up in your, even the formulas, when you worked out the form of it in global ADS as a function of X, I'm pretty certain it's non-normalized.
Oh, no, that's actually not, so that's, there's not, it's secretly not there. It's because in the definition in terms of a mode sum, it's normalizable, but then you use this freedom of adding things that integrate to 0 against O, and the part that integrates to 0 against O has a non-normalizable piece, but it doesn't contribute to the integral.
That's when O satisfies the free equation of motion or the general O?
When O has Fourier components that only come from the free solutions in the bulk, those extra terms integrate to 0.
Yes.
Steve's comment is that if you apply that thing where you've added the extra terms to make it a space-like support, and you integrate against something which has extra Fourier components because, for example, it is the full interacting O from the CFT, those extra pieces won't give 0, and there can be non-normalized terms.
That's true, but then it's subleading in the interactions, right? So it's canceled by the next order.
Also true.
Well, okay. Yeah, you can try to expand order flavor, but still, yeah.
Yeah, so
you have the non-normalizable behavior.
Yeah, so actually, I guess I kind of sidestepped those issues. Well, I guess Gilad and I like these smearing functions that have support on the complexified boundary. And then it's just built into the smearing function. It doesn't matter what you integrate against, you get normalizable fall-off.
But harder to see things directly that way.
To be fair, you know what my comment's going to be. Once you complexify the boundary, you've limited your set of boundary data to analytic data that's analytic in position space. And that's a very small set of data. So I don't want to belabor this point, but this is an open issue to some extent. Right?
Okay, yeah. Yeah, so I guess that's true. I am assuming things are analytic on the boundary, but CFT correlators are analytic where I need them to be, so in that sense I can get away with this. So you get this expression from doing the smearing integral, and you might think that something should go wrong here, because by construction, K satisfies a free wave equation in the bulk. So this correlator is going to satisfy a free wave equation, but this is an interacting theory, so we shouldn't have things that satisfy free wave equations. So something must go wrong here. And indeed it does. The problem is this hypergeometric function has a branch point at chi equal to 1. So that's space-like separation. Since there's a non-analyticity at space-like separation, it means this bulk field won't commute with these boundary operators, even though they're space-like separated. The discontinuity across the branch cut will give you a non-vanishing commutator. So that's what goes wrong. We've constructed a free field in the bulk, but it doesn't respect locality. So what to do about that? Well, I think there's really kind of only one thing you could imagine doing. You have to redefine what you mean by a bulk field. So you say the bulk field at kind of leading order is given by smearing an operator in the CFT. But then if you want to take interactions into account, you need to add a sum that in principle runs over all other operators in the CFT. So these are these operators ON. You smear each one of them appropriately to whatever its dimension is. There's some arbitrary coefficient in front, and you sum over all of these operators. And
so here let me rephrase the question I raised on Monday, and that is, to what extent this is a systematic expansion in a small parameter. And the reason I raise that question is because of what we just said. So the integral of k against O is non-normalizable, so it gets arbitrarily big as you go out to the boundary. It's a big thing. Phi itself on the left-hand side should be normalizable, so it's small in that limit. So you have small is equal to big minus big, and the question is, do you really have a sensible expansion in a small parameter? How do you organize the expansion?
Yeah, I do. Like I said, I avoid all of that. Phi is normalizable.
Right.
I use these smearing functions on the complex boundary, so integral KO is normalizable.
Well,
And as you'll see explicitly, these are higher dimension operators. This correction we're adding actually falls off faster near the boundary than the leading piece.
You could also just choose to use the original smearing function, which is normalizable.
no, that's what we just settled. If you
You
integrate
could choose
k
to do it.
against-
He didn't, but you could.
The original, as Dan means, it means not the one with just space-like support,
Yeah, no,
but
the
the one
one
which is defined by Fourier transform over the entire boundary.
That's correct.
That
Yes.
does something different.
You need
That's
yeah.
doing something different. It was, well,
That
yeah, I'm
one
not
is
sure what
normalizable.
you
It's
would
defined
have
by a
in
mode
those.
sum.
Yeah, I mean, do you have to enter it by going to the complexified boundary? I mean, could you say in particular you have these very explicit smearing functions as a Poincare patch,
Uh-huh.
for example, and so that K could go over the entire boundary of the Poincare patch.
Right, and then those are just normalizable.
Yeah, so you could work with smearing functions that have support on the entire Poincare patch. I guess you could do that. Probably one could reach the same conclusions that way. These complexified smearing functions actually are kind of nice because if you actually want to do this calculation, what does the smearing function do to a 3-point correlator? So the way we set things up on the complexified boundary, you can do this calculation because what you do, you go to a place where the support of the 3 operators is space-like separated, and then the CFT correlator is some nice analytic function. You can do the integral with no problem. You get this hypergeometric function. If I used a smearing function that had support on the entire Poincare patch, I don't know, I'd have kind of unpleasant overlapping operators in the CFT. I'm not exactly sure how I do that calculation. Maybe there's a way of doing it if you work hard enough, but I've never really tried.
So the way you know how to do it is with the complexified boundary, and if you don't want to do that for whatever concerns, then it's not clear quite how to organize it as a systematic expansion. Is that correct?
No, I think it's fine. You can just use the good one. Do what he said. Use the Poincare smearing function. It's manifestly normalizable, and then just use the Hum's expansion to generate the corrections.
But did you say you were concerned about what the integrals do with as O2 approaches O3 as the operators approach each other? Was that the last thing you said? You said there was a concern about.
Oh, so since these complexified smearing functions have compact support on the boundary, I can go to I can put my operators where the support of these three things is at space-like separation.
Yeah.
And then it's a nice, well-defined integral.
Okay, but I'm not sure that's ever a problem in the following sense. So what you have in there is, okay, you end up with, although O2 and O3 are time-ordered, the actual products on the boundary are Whiteman functions. They're not time-ordered. And I think those are good as distributions. They're integrable against a smooth function. So there actually is no potential for a divergence from collision of operators.
Like they're integrable against things that are not in fact smooth, but are singular in just the right way. And these smearing functions are just the sort of
Yeah, I think that should. Okay, yeah. So that, maybe that should work. Okay, well, so we have this this result from the lowest order calculation that violates locality in the bulk. We want to add this tower of higher dimension operators. And so now it's a math problem. Is there a way to choose the coefficients in this expansion that will restore locality in the bulk? And I claim there is, that as long as you work in the 1 over n expansion, order by order in 1 over n, you can fix these coefficients to achieve bulk locality. So just as a simple example, I guess I'll return to ADS2 CFT1 with dimension 1 operators. So there's an operator in the CFT. It's a single trace primary operator. And if I want to work to order 1 over n, what are the higher dimension operators I need to consider? These ONs, they'll be double trace operators built from 2 factors of O plus 2n derivative operators. So this is an operator that has dimension 2 plus 2n. And then let's start calculating commutators. So I can take my single trace operator, I smear it into the bulk, I take a commutator with an operator on the boundary, and I put that commutator inside a 3-point function with some other operator on the boundary. So this is basically the 3-point, the bulk boundary mixed 3-point function I wrote down earlier. For ADS2 and dimension 1 operators, that turns out to be some Legendre function of square root 1 minus chi. So that's the commutator that you pick up from just the single trace operator. And it's non-analytic when chi goes to 1. You've got this square root singularity. You've also got all of these higher dimension operators, these ONs, that are double trace. You do the same calculation with them, take the commutator inside a 3-point function. It turns out that commutator is given by Legendre polynomials of order 2n plus 1. So these guys also have square root singularities as chi goes to 1. So now the mathematical question is, can you superimpose these higher dimension operators in order to cancel the singularity we got from the single trace guy? There's a very nice formula that the Q0 Legendre function is given by a sum of all the odd Legendre polynomials. So the coefficients in this sum, these are basically the coefficients an that you need to stick in that will let you cancel the non-locality at lowest order against all of these double trace operators. So there are there are normalization coefficients that you need to keep track of as you go through all of this. But you would do that, and you can do that and keep track of all of the normalizations. And you can get explicit expressions for these AN coefficients, the AN coefficients that you need.
So sorry, you have in mind a kind of probe sector that's internally consistent by itself? The cancellation has to work within the sector, this O and its derivatives, is that? As opposed to coupling to other fields, maybe this.
Oh, okay. Yeah, so what I'm doing here, I'm starting from a particular 3-point function in the CFT, and I'm trying to lift one of those operators to be a local field in the bulk. So I'm doing this construction for one particular 3-point function. And that's one of the, I think, open questions. Can you make this work for all 3-point functions simultaneously? Or what's kind of the same thing? Can you make it work in a 4-point function? So there is more work to be done in that direction.
Maybe related. I mean, this will work for any CFT with a large N expansion. Vector-like is a garbage. I mean.
No, actually.
No. What goes wrong? Right, but this is where's the?
Well, for example, those O's that you need to have the only light operators, right? So in general,
where's that?
So he's assuming that those O's are multi-trace operators whose dimensions are just integers times the dimension of the single trace one. And if there were other operators around, they would mix in the OPE. And so what you need is you need the 3-point functions in the CFT to be consistent with what you get from Feynman diagrams in the bulk. And that won't be true if there are other low dimension operators sitting around. Like if you have like a dimension 10 operator that doesn't, come from some weird stringy.
So this particular criterion you're saying would be satisfied because he just showed it explicitly.
Yeah, where's that?
However, that's not enough.
Well, in this model, he assumed that he's making assumptions about the OPE, right? Like he said the 3-point function is something in the CFT.
Are we talking about higher point function? I mean, the 3-point function.
Yeah, this is the 4-point function.
Yeah, no, I mean talking about the 4-point.
Yeah, but this 3-point function argument depends on nothing.
Yeah.
But the 4-point this will show up at the 4-point.
Yeah, because these other operators will show up in the OPE.
Yeah, but that's the test.
That's right. At
This
the
is a very
level
mild
of
test.
At the level of 3-point functions, you need the 1/n counting, but that's pretty much it.
Yeah, so this is almost kinematic or something. So this is not.
Well, you do need a large N. You need all these function trees operators.
Right, but that's very mild.
Yeah.
So a couple of things I'm not understanding about this. So far as I can see, you just showed us commutation between this thing and boundary operators, right? But in a local theory, the different bulk fields and space-like separated bulk points would also have zero commutation. So I'm just asking, that's an additional thing that one has to build in, or what is?
Yeah, that's true. I think. Let's see. So, I think checking locality with all of your boundary operators is probably enough to guarantee that you've got locality even for two points in the bulk.
I don't immediately see that argument. I'd like to see it if everybody understands that it's true.
I don't want to derail the talk, but I think it's because you can solve the equations of motion in, right?
Sorry?
You assume that the boundary correlators are given by Feynman-Witten diagrams in some local theory. And then if that's true, then if you solve the operator equations of motion in, you know that the local theory operators just are constructed in the same way, and you know that those commute, so these will too.
That's true, but that's an ingredient that I'm trying to avoid using in this construction.
I understand.
I think this should be sufficient. But that would be a good thing to check.
Now, when you say soluble in 1/n expansion, you mean leading order in the 1/n expansion, right?
The work that we've done is just leading ordering.
But we just had a discussion a little while ago in which you said you expect the fields to be non-local in the gauge that you've chosen in the bulk.
He means you get the right commutators, not that the commutators are 0.
Oh,
Yeah.
okay.
Yeah, that's right. Yeah.
Going back to the previous question, which is restoring locality at order 1/n. Now, if you go to at 1/n square, then maybe we can make the 4-point correlator local. But there will be a loop contribution from the 2-point function as well, which would be 1/n squared. Then how do we know that we'll be able to cancel both the 4-point contribution and the 2-point loop contribution?
Yeah, so that's a good question. I think that's one of the kind of open issues that when you go to order 1/n squared, as you said, on the bulk side, there'll be loop diagrams. And it's an interesting question how this procedure of bulk reconstruction, how it handles those loop diagrams. On the bulk, you kind of know what to do. You know you have to renormalize. How does that show up in the CFT? Pieces of it you understand. Operators in the CFT should acquire anomalous dimensions. So you should, I think you do need to go back and correct the dimensions of your operators order by order as you work in 1/n. I think it's an interesting question how you actually do all of that in practice.
To what extent do people attack or look at the 4-point function? What's the status? Has that not been looked at all?
Hasn't really been done.
Well, I mean, there are calculations of 4-point functions from Feynman-Witten diagrams.
Yeah.
And they show the renormalization effect you just talked about of the double trace operators, right? There are logs in those correlators that Witten explained correspond to the renormalization of the double trace operator.
No, but I'm thinking about this program
No, this program.
Yeah, this program hasn't gotten to order 1/n squared.
Yeah. Okay.
So there are. So let's see. Well, okay, good. So in this way, we're able to build a field in the bulk that's local to order 1/n. But still not quite satisfying because we'd like to say a little bit more. We'd like to say, for example, what are the bulk equations of motion? And the concern is we've developed this expression where our field that's now local in the bulk is a smeared operator plus an infinite sum of smeared double trace operators. And that's not the way that we're used to thinking about a field from the bulk point of view. So we'd like to say, for example, what kind of equation of motion does this object satisfy? And it turns out it's not too difficult to work it out. So here are the steps. Let's take this expression for our bulk field. And this was a massless field in the bulk. So let's act with the massless wave operator. So on the left-hand side, we get box of phi. On the right-hand side, the first term in this expansion, k there by construction satisfies the massless wave equation. So box will kill that guy. All of the higher dimension operators are smeared in the way appropriate to their mass. So these satisfy the free wave equation for a field of mass appropriate to their dimension. So when you act with box, box on this just gives you a factor of the mass squared for that, whatever the dimension of that operator is. So you get a sum, these coefficients that we've determined, the mass squared corresponding to all of these different operators times the smeared operators. So still, from the bulk point of view, this kind of sum is not a very familiar looking object. We'd like to identify what it is in terms of bulk quantities. Here's a way to do that. Let's take this quantity on the right-hand side. It's a CFT operator. Well, it's an infinite sum of CFT operators. Let's stick it into a CFT correlator with two other operators. So what you get is basically an infinite sum of mixed bulk boundary correlators. It's that same hypergeometric function I wrote down earlier. You need to do the sum on n. You do that and you get a pretty simple expression. And what you get, it factorizes. And each of these factors is actually a bulk boundary two-point correlator. This first factor is the bulk boundary correlator for a bulk point with a boundary point x2. This other one is the correlator for a bulk point with a boundary point x3. So, in fact, you can identify from the bulk point of view what this right-hand side is. It's just the square of your bulk field. So you just stick phi squared in here. You get a product of two bulk boundary correlators.
Did you say you have a tree-level correction to the mass of the field in the bulk? Bouncing it off the boundary?
No. So I've identified this is going to be the equation of motion for a bulk field.
Right. So it has a mass. Oh, sorry. That's a cubic term. I'm sorry.
Yeah. So box phi goes like phi
course.
squared. We have a phi cubed field in the bulk. And again, if you keep track of normalizations, starting from the CFT 3-point correlator, you can figure out what the phi cubed coupling in the bulk is. Yeah.
Sorry, I'm confused about something very basic. Conceptually, all you have so far used for the sort of reconstruction was just the bulk geometry. But where is the input that gives you the information to extract the dynamics?
So I did start with a CFT 3-point correlator, and that encodes information about the dynamics. So that's where it came in.
Well, a related question, you're sort of, well, the input from the bulk is basically the smearing function. That's the thing that's the place where you bring in bulk data in a sense. Or at least, no, he's reconstructing that. Right?
Yeah, you determine that.
Yeah. So he's not starting with that. He's following that.
But then the smearing function is just solving equations from that Lagrangian, so it's not.
So they do more.
The smearing function is group theory, right? It's realizing that.
Yes,
That's right.
That's good. Yeah.
Where does the particular CFT enter?
So the particular CFT, the dynamics come from at this order come from the 3-point correlator in the CFT, and that's fixed by conformal invariance up to an overall coefficient.
Are you saying that any CFT gives at that order a phi to the third theory? Or are the coefficients different? Are they CFT different?
So the coefficient in the CFT 3-point correlator would determine the coefficient of the bulk phi cubed coupling.
Is it really just local like that? It isn't some complicated thing?
In the bulk, no, we recovered a local bulk interaction
To this order.
to this order in 1/n.
And it's not unique bulk Lagrangian that would give this? Because you could make a perturbative field redefinition of phi.
Let's see.
Like phi go to phi plus g phi to the fourth.
Yeah.
And you have some theory in the book for which miraculously you only get the 3-point function at this order. So there's some. This is like trying to reconstruct a Lagrangian from the S matrix. It's not unique.
Yeah. So maybe.
What you've given is sort of the simplest approach. And I'm not saying it's not a good one.
Okay. Let's see. Well, let me skip ahead then.
Having written down that equation.
Oh, sorry.
And having solved it in some way with some given ANs and ONs, either it satisfies that bulk equation of motion or it doesn't, and there's no more opportunity for field definitions.
I'm saying there's another bulk equation of motion that could yield the same 3-point functions.
That will be true,
Yeah.
but that's saying that there's the solution he wrote down on the top line is actually not unique.
Correct. Good. Yeah. Good. You're both right.
Question. One way to see that non-uniqueness is actually you can instead of using local double trace operators, you can use bilocal fields, bilocal products of single trace operators. So you can do a double integral instead of a single integral, and that's in fact from the equation of motion that you're getting at the end. You can see that you must be able to write it like that. Is there any advantage to starting with that assumption and enforce micro-locality on the previous slide that say we write down instead of this KNON, simply write down some double integral by local field.
Yeah. So if you solve the bulk equations of motion perturbatively, that's kind of guaranteed to give you bulk locality. And it naturally leads to these expressions where at order 1 over n you add bilocal corrections to your field.
I want to say, let's start with a bilocal assumption, but not assuming a local equation of motion at the moment, but derive it using the same methods. I think it would succeed.
Yeah, probably. You probably could start with some bilocal ansatz and
because your double trace operator is simply a Taylor expansion.
Yeah, that's right.
So it's the same amount of information put in.
Yeah, I agree. Yeah, it'd be interesting to see if you could start with a bilocal ansatz, and maybe it's easier. So yeah, there've been some questions, and this is something that Tom Banks raised as an issue a while ago. You could object to this on the grounds that there must be some ambiguities in this reconstruction of a bulk theory. And I think you can see this both from the bulk side and from the CFT side. So on the bulk side, you're free to take some bulk theory and make local field redefinitions in the bulk. That will change the Lagrangian, change the equations of motion, but it really leaves the theory invariant. In flat space, it would leave the S matrix invariant. In ADS-CFT, I think the statement would be that the CFT correlators that you extract from that theory would be the same. So we have that kind of ambiguity about the bulk theory coming from the bulk side. What I'm going to claim is that we actually have exactly the same ambiguity on the CFT side. Because we chose all of these coefficients in front of higher dimension operators in order to cancel some unwanted non-analyticity that spoiled locality. But that procedure isn't unique, because on the CFT side, I'm always free to add a tower of higher dimension operators that don't spoil the analyticity properties, so that things still commute at space-like separation. And so what I'm claiming, I guess, is that these two ambiguities are in one-to-one correspondence. And I think it's pretty clear, because if you start on the bulk side, So imagine you have some local field in the bulk. If you make a field redefinition like phi goes to phi plus phi squared, since what you've added to your bulk field is a local operator, such an addition to your bulk field will commute at space-like separation, say with boundary operators. So such an addition won't spoil the analyticity properties that we wanted. Or kind of conversely, if you come up with some combination of CFT operators that you can add that don't spoil analyticity, kind of by construction, such a combination acts like a local thing in the bulk. It commutes at space-like separation. You should be able to think of it as a local field redefinition in the bulk. So I claim that all works out. The ambiguities that are associated with field redefinitions match the ambiguities that you encounter in trying to reconstruct a local field in the bulk. And, well, I guess just as an example of the sort of game you can play, if you start with, this would be the equation of motion for a phi cubed theory in the bulk, and you make a local field redefinition, it turns it into a theory that has a different phi cubed coupling, but also has a derivative coupling. And then this has kind of been I think shown in the literature. If you take a theory like this in the bulk, and you calculate Feynman-Witten diagrams and take them to the boundary, they give exactly the same boundary three-point functions that you'd get starting from your original theory. So I think that's a consistent story. There are some generalizations that maybe I'll mention. Most of the formulas that I've talked about are for ADS2, but you can play the same sort of game for scalar theories in higher dimensional ADS, scalar fields with arbitrary masses. We've also considered scalar fields in the bulk that are coupled to gauge fields, coupled to a conserved current on the boundary. In that case, you can play the same game. You start with the three-point function between two scalar operators and a conserved current on the boundary. You try to lift one of these scalar operators to a local field in the bulk. You can do it by adding higher dimension operators. You work out what the equations of motion have to be, and you get the right coupling between your bulk scalar field and the gauge field. It also works for a scalar field coupled to gravity. Then you start from the correlation function with a stress tensor, so OOT. Promote the one of the scalar operators to a field in the bulk, and you recover the right coupling to the bulk metric perturbation. So I guess those are the generalizations that we've explored. There are some things which...
well, actually, going back to that, so you're reconstructing the bulk fields, not the dressed bulk fields, or what? Yeah, what are you doing?
No, they will be the dressed.
These are the dress.
Oh, they are. It is with the okay, yeah. With the dressing.
Yeah.
Why they don't have fuzzy.
So, for example, to put this scalar field in the bulk, you need to add higher dimension operators, which are double trace, and they're built from the scalar field plus a stress tensor. So it's exactly the gravitational dressing that comes in. Yeah.
So why not apply this in practice to theories which would have the cilia in the bulk, and then work out 1 over n, what the action is in the equation of motion?
Yeah, I think that'd be. Yeah, that's an interesting project.
Is it? You think it? So you think there's an obstacle, or at least difficulty of going beyond? I mean, you did spin 1, spin 2. What happens at spin 3?
Yeah, I don't know. We haven't we haven't tried to do spin 3.
But we don't expect that to be local.
That's one of the challenges that I'm not sure what sort of locality properties you'd want to enforce on a higher spin theory.
But also here to higher order, you don't have exact micro-locality, right?
Yeah, but that's a
Because
lot
the
worse.
gauge is- Well,
Yeah, so
Comprehensible by mortals, right?
yeah, so what you do, so for example, to make this charged scalar field, since it's charged, it's not really local in the bulk. It has this Wilson line tail that goes off to infinity. So what helps is the fact that so the scalar field isn't local with respect to the electric field in the z direction, but it is local with respect to f mu nu with indices tangent to the boundary. So that's actually the condition that we impose. So you make it local with respect to f mu nu tangent to the boundary. That's enough to fix the coefficients. And then you go and check what's the commutator with f mu z, and it comes out to be exactly what it should be by the Gauss constraint.
I see. So you actually think there will be enough real locality constraints where I don't have to sort of know the bulk Lagrangian and what the non-locality looks like in order to fix all of these things, and then the non-localities will just come out. That's the claim.
I hope so. That works for E and M. For gravity, it's a little shakier. To this order in 1 over n, we found some components of the Weil tensor that respect locality, and
then you found the correct non-zero commutators with
yeah.
So that did work to that order. That's impressive.
Yeah, and it's all it all works very nicely. So so for these charged scalar fields, the higher dimension operators that you add, they're scalar operators, but they're actually not primary fields. And what that means is the field in the bulk that you build, it doesn't quite transform like a scalar under ADS isometries. But that's also exactly what you expect, because if you act with an ADS isometry, it moves the Wilson line, and then you need a compensating gauge transformation to put the Wilson line back in the z direction. So the field has an anomalous phase under isometries, which is exactly the fact that the corrections you add aren't primary.
I'm confused about this Wilson line. So this phi is some local bulk field, and then you say, well, you have to obey Gauss's law, so you have to add some Wilson line. Now, isn't it actually a physics choice? You know, whether I add the somewhat spherical symmetric field, or all right. So then you're making some particular choice of addressing there,
Yeah.
which is a single Wilson line that goes.
Yeah, that's like the axial gauge condition.
Yeah, it's
Well, if it's a gauge condition, then it's not physics. So my
It
question
is-
is,
well,
In
it corresponds to
some
making a
gauge,
physical choice of Wilson line. It's in one-to-one correspondence with making that gauge choice.
when I insert a charged particle at a point, I can choose various different ways of satisfying Gauss's law.
Yeah, that corresponds
those are
to
different
making different
operators.
gauge
Those would be
choices.
different operators.
Those are different physical operators.
Exactly, they're different physical
So he's
operators
picking
that are
one.
not related by gauge choice.
Yes, that's
That's
right.
absolutely
Okay.
right.
So he picked one which in axial gauge looks simple.
Okay.
But they're all such that they would give the same scattering matrix.
Yeah. Yeah, and if you computed a gauge invariant operator, the dressings would cancel. Like
Well,
if you computed phi dagger phi.
Yeah, in electrodynamics.
In electrodynamics. In gravity, less clear.
No, actually, I don't think that's true.
I think phi dagger phi is the same.
Sure.
at the same point.
Of course, at the same point.
Yeah, but in a general scattering amplitude, I think it depends on which.
No, I mean the local operator phi dagger phi.
Yeah.
You can choose, for example, in non-abelian gauge theory, choose axial gauges in different directions. Choose to use the physical A components in those different gauges as interpolating fields. You'll die before you actually compute all the Feynman diagrams, but you will find the same answer no matter which gauge you chose.
Well, actually, related to this, and actually this connects to the stuff Will and I have been doing. If you create phi, with the Wilson line that goes off to infinity in the z direction, so that is a physical choice, a physical field configuration. And in fact, if you evolve it, what happens is it basically radiates away. So you get radiation at infinity from because the optimal field configuration is not to be all, have the flux lines confined all going along a small tube in the z direction. They want to spread out and be the Coulomb field. And in the process, you get radiation at infinity. So in fact, if you use different operators, I think you'll get different, say,
Phi dagger phi is a gauge invariant local operator.
I'm not saying, but I'm not saying compute phi dagger if you have a 4-point function of the phis at different points. Say if you're computing an S matrix.
You'll get different answers, but if you go and compute the S matrix, you'll get the same answer.
No, not for the different dressing.
Look, you take the axial gauge. I didn't tell you which direction to take the axial gauge in. Let's go compute the S matrix in the axial gauge in the standard model. Okay? All the non-abelian fields are massive. There's a real S matrix, no infrared issues except the usual electrodynamics ones. I'm working in axial gauge. I'll get the same answer for the S matrix no matter what direction I put in. The S matrix will be Lorentz invariant.
So maybe just to conclude, a few kind of open issues, open questions, and some of these points have already come up. So I think one question is just if you try to push the 1/n expansion to higher orders. At order 1/n, we only had 3-point functions, and aside from using 1/n counting, it seemed this would work in pretty much any CFT. If you try to impose locality at the level of 4-point functions, you might find more constraints. And in particular, you might find that there were constraints on the CFT spectrum that have been discussed in the literature and in Liam's talk. Another issue that one would have to face at order 1/n squared. At that order, you start seeing bulk loops, bulk renormalization effects. How do those come into this program? How do you take those into account? These questions, I think, are interesting and kind of worth working on. They're the sort of questions that, with some effort, I think one can kind of plow through this stuff. But in a way, the kind of bigger prize is trying to understand what happens at finite n. And there's been some speculation about this in the literature, some work that I did with Gilad. Papadodimas and Raju have talked about these things, and also Steve has some related speculation. I think most likely, at finite n, this program actually just crashes. That there's no way to actually build local bulk fields at finite n. And so I think if you start with a finite n CFT and have kind of real quantum gravity in the bulk with finite Planck length, I think you're going, well, you could still define fields in the bulk, But I think you're going to have to live with non-local commutators that probably are of order e to the minus n squared.
What specifically crashes, say if n is huge but finite, what specifically are you saying crashes with what you've done so far? How do you see the crash?
Yeah, so this business that if we started with a single trace operator, we could make it local by adding all of these double trace operators with the right coefficients.
Yeah.
So to get those coefficients, we did need to use large n counting.
Yeah.
We calculated all of the correlation functions using the 1 over n expansion. And at finite n,
well, so I'm arguing against what I was saying earlier, but no, I'm just trying to understand and look at it. But well, okay, so maybe it doesn't converge, but you could at least develop formally an expansion in 1 over n.
Well, the operators stop being independent, though, right? Once you have order n of you don't get to change their coefficients independently.
Yeah, so at some point the expansion goes bad, but it could be like QED or something where we have a good expansion, that works out to some number of orders.
Yeah, that's why he wrote it e to the minus n squared.
Yeah, okay.
It might be some kind of asymptotic expansion,
that type
and
of
you'd be left with the effects of order e to the minus n squared.
What would that mean in terms of measurable non-locality? Like if we tried to tell our experimental friends, if you push down to 10 to the minus 18 meters, if you just push down to 10 to the minus 23, how would we?
Well, so this would be an effect that's non-perturbative in Newton's constant. So it'd be non-perturbative in the Planck length.
And in the ADS scale. I mean, if you thought about this at a Minkowski space limit, they might be 0. And if you thought about this in a limit where you turned off the cosmological constant, that might just be 0. It might be even minus infinity. At the level what's written here.
So the effective coupling is the wavelength we're considering in Planck units.
You think that n is something which is more...
Yeah, it's the wavelength we're considering divided by the Planck length.
I mean, that's a reasonable guess, but is that something that comes out of this calculation in some clear way?
Well, it's the effective coupling in gravity, so we're assuming that this is...
Yeah, I'm sympathetic to that idea.
I'm confused on many levels by this estimate of how big the commutators should be.
Yeah.
So this 1 over n expansion is a weak coupling string expansion. That's how we think about it. So there are operators whose dimension scales to infinity with n, okay, whose contribution comes in at the string scale, and those should violate locality because ordinary perturbative string theory doesn't have a local field expansion. And then if we're talking about non-perturbative effects, Steve argued that 1,000 years ago that there are e to the minus n. It was 25.
But also from the bulk perspective,
Those might be tiny though. D-branes are small. I mean, maybe those aren't the big non-locality things. I don't know.
But there's some violation of locality of that order, at least. But just perturbative string effect should violate.
Well, presumably you run into trouble on the I guess your second line is. I mean, if you have a big string length, then you go home. So you want to push the string length to be of order the Planck length to be happy.
But then you're not doing the 1 over n.
Well, you're doing whatever flat space limit.
You do like ADS 4 times S7, right?
Right, or pick some.
Okay, all of this stuff was standard 1 over n counting. It was not the low energy expansion, right? This was sort of saying, I have a dimensionless parameter for arbitrary momentum, okay? And I'm expanding. He hasn't talked about the alpha prime expansion here.
But don't
He
you
said I have a gauge.
But trading the 1 over n expansion for the G string expansion.
I think he's in the flat space.
Yes, that's what I'm saying.
His lambda is of order n. N over lambda is fixed, right?
Well,
That's
that's the way you cure the third line.
Yeah.
You do that. So you find you do that when you run into that trouble, and then you do that. And then you still probably have e to the minus Planck length, I don't know, whatever the suppression of making a black hole.
But that's m squared.
No, but again, let's call it out Planck then.
Well, wait, I think from the bulk point of view, you expect to have big effects, when you say make a bulk black hole, say in a high energy collision, and that's not e to the minus n squared. I don't think it's not suppressed. It's an order one effect when you collide enough energy in a small enough region.
Yeah, but he's not doing that. He's doing low energy.
No, well, okay, yeah. So if you consider these things with sufficiently
these are like
high
off-shell
energy,
black holes or something.
yeah, but what about the on-shell ones? You would have a similar breakdown of you would expect
he's
of
not doing
locality.
that, though.
He was going to say something.
Well,
The energy length is one of the lengths.
Do you have another transparency?
This is it, actually. So I think actually the place where our estimate for these commutators is maybe best understood is actually by trying to look at what happens if you try to reconstruct local fields in a black hole background. And then we know something about finite n correlators in a thermal CFT, and we can translate that into a statement about these commutators. And then the suppression factor is e to the minus entropy of the black hole. So that's the setup where I think they're best understood or under the most control. There's.
Dan, that's for an expectation value of a commutator in a thermal state at high temperature?
That's right. I guess, yeah.
Is there any chance that those fundamentally non-local effects would be big enough to explain the rising problem without inflation?
Well, I don't know. It's true you might think non-local effects should be there in cosmology, and what kind of effects they might have.
If you didn't believe in an early phase of accelerated expansion, you would say we already have seen horizon correlators. If you had a fundamental theory that produced them, that produced them at the right scale, I don't know whether it does or not. Is there any chance that it might?
I don't know. I mean, I don't know. It would be interesting to see how these ideas play out in a cosmological setting.
So, can I ask a question about the black hole story? The standard understanding in the CFT of the black hole, the Hawking phase transition, involves all of these states which have very high dimension. They have dimensions of order n squared, and it's very, very dense spectrum, and so on. And to what extent, I mean, those states don't satisfy large n counting rules at all. But you're somehow saying that despite that, you would expect in that background to be able to have local fields that satisfy the usual.
So this would be trying to carry out the construction perturbatively around a black hole background. So you take a black hole background and then try to construct perturbative fields around that background instead of around MDADS.
Sure. Tom, if we compute Euclidean correlators at finite temperature, I guess we expect that the correlators factorize in some limit at least.
Sorry?
So we can look at the correlators in the thermal trace, so Euclidean correlators at finite temperature, and then I guess we expect that they factorize in a particular limit when the separations are not very large. And then we know that typical microstates, correlators on typical microstates should be close to correlators on the thermal ensemble. And this implies that the correlators should approximately factorize even around the pure state, the typical pure state, at least when the separations are not very large, I think.
to me that this is the wrong question at finite n. I mean, everyone's still talking about fields on some fixed space-time background. Right? But finite n is real quantum gravity, and the metric is fluctuating. There's some wave function, superposition of metrics. And so why are we talking about whether operators can use different space, like separation?
There's a regime, even at finite n, in the real world, that's approximately true, right? In our description via field theory of the real world. There are regimes where you have small gravitational effects and regimes where you have big ones with finite gravitational coupling.
This is perturbative canonical gravity, so the metric is fluctuating perturbatively.
But it's not perturbative at finite n.
Well, at large with finite n, it's a not bad approximation to do perturbation theory.
Exactly.
This n
In
probably
low
is a lot
energy,
bigger than
etc.
1 over 100, 137. Right?
Yeah, it's like doing perturbative QED.
Exactly. So I think what Gary is saying is that if we are looking at this accuracy, we could have a gravitational instant and that moves these 2 points just next to each other, for example.
Yeah, especially that.
No, so the claim is you just don't believe anything at that size. Right?
That's correct. That's a better way of asking my question.
Yeah.
I mean, it's not just that it's that level of precision you'll never get. Right.
Well, that's true. Well, let's see. So working from the CFT side, you can try to construct local fields in the bulk and ask, to what accuracy are you able to carry that out? And I think it breaks down, certainly by this order. And then you could also try to understand this from the bulk point of view. Is there some non-perturbative bulk gravitational physics, which likewise violates locality? There are all sorts of bulk effects that you could speculate about. So I don't know, maybe it's too much to hope that there'll be any kind of matching.
Put differently, well, there are different ways to try to reconstruct, bulk gravity. What is our target? And, one target is a set of observables with some algebra that they obey, and it may not look, like exactly the algebra of local field operators. You would expect it to, in fact. But nonetheless, you could try to identify those operators and see the size of the corrections to what look like the local relations.
So I have a very basic confusion that's related to what Gary just asked. Suppose you are trying to run this program for bulk gravity with stress tensor. You talked about field redefinitions. So I could imagine doing field redefinitions to the gravity, to the bulk metric. So when I try to look for locality, with respect to what metric am I supposed to look for locality?
Let's see.
You're always doing perturbation theory.
Is that the out? That is a well-defined background light cone that defines everything for me?
I mean, at least in these 1 over n expansion stories, for sure. Once you start talking about what happens at finite n, then I think you guys all disagree with each other, and I disagree with all of you.
Sadly, the nature of this field.
Anything else? Thanks very much.